A creek that runs past my house that's prone to flooding, and it wasn't over the banks yet, so hopefully there aren't too many people who are stuck. But if it continues like this for too much longer, it probably will get over the banks and onto the road. Just as a reminder, now that you've submitted homework 7 today, the next thing on your plate is the Phase 1 submission for the design project, and that's where you are thinking about how much water is required at each of those green arrows on the project map. So I'm going to go over an example that was submitted last year that was it's an example of somebody who did a nice job, and we'll look at some of the characteristics of that. I also wanted to point out that on that printed map I gave you on the day of the exam, you know, the one that's 11 by 17, it says down at the bottom on the left side that 1 centimeter equals 100 meters. And so what that means is if you have a ruler that's graduated in centimeters, what you can do is you could measure out some length on that map, and let's say it was 8.5 centimeters is what you measured on the paper, then that would mean it's 850 meters in this hypothetical location where you're designing the pipe network. So every year, most people get that, but a few people don't make the connection that that's a scaled map. So then beyond the submission for Phase 1, which is due on Monday of next week, then on Friday of next week is homework 8. And the assignment that you submitted today, I think I described that as relatively easy, and I wouldn't describe homework 8 as relatively easy. So it's got 10 problems. It includes some Mannings equation with trapezoidal geometry where you're solving for depth. And we'll do 2 of those examples today, so I think you'll have like a good pool of experience to draw on when you're doing homework 8. But I would not suggest wait until the last minute to start that one, just because it's a little bit more lengthy and some of the calculations are a bit more detailed. So I wanted to give you some advance notice about that one. So today we're going to continue talking about Manning's equation, which is the formula that we apply when we're solving problems related to steady, uniform flow. Steady flow being that conditions aren't changing over time. Uniform flow being that conditions aren't changing in the direction of flow, so that the channel is prismatic. Any questions related to the announcements before we look at that student example from last year? All right. Well, let me show you this. This student got a 20 out of 20 on the submission. They weren't the only one who did. There were others. So you don't necessarily have to do everything that this person did, but it's just an illustration of some of the good characteristics. So you can see that their submission started off with the standardized demand forecasting summary table. And I'll tell you the reason why I ask people to present it in this way is I'm going to be grading 20 plus of these submissions, and you can see that this one is 21 pages long. Not all of them will be. This one was. And so I need to have everything summarized at least in one location in a really succinct and standardized way, because I know for each student approximately what sorts of flow rates are reasonable. There's a range of realistic values, and so if you're outside of that range, then I'll pay a little more attention to what your assumptions are, and they could be that your assumptions are fine and that it's just your city has maybe unique circumstances that differ from the standardized ballpark estimate I've developed. But having this standardized reporting system allows me to do that, to hone in on when somebody's there versus not quite there. So it's clear enough. I guess if I have a criticism, it's a little bit silly to report the flow rate to the nearest thousandth of a liter per second. That's probably not necessary when these estimates are based on so much speculation to begin with. It would probably be okay to say like 23.4 on this page. It doesn't need to be 23.433. Anytime you are writing down a final answer to some series of digits, 5 series of digits, what you're basically claiming is that you are measuring everything with enough accuracy to make it worthwhile to report it to that precision. And that's not the case here. If you're saying, well, the average American uses about 220 liters per person per day, if it's a ballpark thing like that, then your residential demand isn't going to be known to the nearest thousandth of a liter per second. So it could be improved on, but it was good enough for a 20 out of 20. So we'll just scroll down a little bit here. Not much to say about the summary page. They did it the right way. Okay, here are the hand calculations. And some of the things I like, by the way, this person doesn't have perfect handwriting. A lot of people have better handwriting than this, but it's clear enough. I don't have to go and get a translator or like somebody who specializes in Egyptian hieroglyphs or something to penetrate through the handwriting here. It's good enough. I like that they've spread it out. Paper's cheap. It's like less than a penny a page. And so there isn't any, you're not sending this to me on a Raven, like with tiny little scripts where it's going to have to be wrapped up in the leg of a bird. So let your solution breathe and don't cram too much stuff too closely, because it just makes it harder to understand what's going on. But some of the things I like about this calculation is it's really clear which area of the project they're working in. So north zone, length on map, the units are included in every step of the calculation. So it's the formula, then the substitution with the units, then the result of the calculation. I just found this really linear and logical. So part of the logic of it is that they're starting the presentation of the calculations in the same order that the forecasting table is. So if all of a sudden they just jumped in on the first page at the box factory, yeah, we do have box factory calculations, but why not present it in the same order that the summary page is presented? So just think in terms of, is there a way to be standardized and logical, neat, detailed, and thorough? So in these calculations, I think there are a couple of places where this person identifies what's the source of the data that they used for the assumption. And remember that there is a written portion where they go into some written detail about the references and the thinking, but it's okay to also here say, from what source you got the data. Maybe it was from, the city water department or something like that. So we just keep going with the calculations, and the units conversions are easy to follow. There's just no shortcuts in this, and so I appreciated that. And it's always clear what area the calculations are referring to. And then when this person is done doing the south zone calculations, this nice thick black line makes it clear that, the area calculations are complete. They've determined the population, and now we're finding the residential demand. And so things don't bleed together in a way where I'm never quite sure what phase of the calculations we're working on. It's very distinctive. So let me scroll down to now the write-up. All right, so some of the good things about the write-up is that the write-up is also presented with really clear sections. If it was one continuous paragraph without headings like North Zone, South Zone, I like the headings because it mirrors everything that we've seen so far in the summary table and in the supporting calculations, so that's good. You'll notice that references here, they're using a standardized method for the references. I think that this approach of just citing it with a number is better than just pasting the entire hyperlink of a website into the body text. So you could use author date, or probably this method of just a number in brackets is the most efficient way, because at the end of the report, they've done a nice job of saying what their sources are. And it's more than just a link. It's not just a hyperlink. It's who is the author? What is the date that it was accessed? What's the title of the web page? This would be the date of publication, and this was the date that it was accessed. And so, they're following a standardized method for referring to information, because I may not want to, if all you gave was the link, yeah, I could go to the link, but maybe I'm just wondering who generated the data. And this makes it clear it's the Department of Public Works. And you can give me that information without making the reader click through, load the page, download the document, and go and find from themselves who the author was. And that's like a pretty standard thing that you provide when you're providing citations is who is the source of the data. And this isn't a list of references consulted. I don't need to see a list of references consulted. I want to see the references that you're actually citing. So it should be that here in the write-up, there's a specific citation to a certain amount of information. So this looks like this is something about US Bank Stadium. There's certain pumps in the stadium, flow rate, and so on. So this is just information about a stadium that they researched to get more details about how much water the stadium in their project is going to be consuming. So again, you're not just pasting a link in there in the text of the write-up, and there should be a direct correlation between the references that you speak about in the body text and those that are listed in the report. Don't include citations, or don't include references that you don't actually quote in the body text. That's a standard component of technical writing. Anybody have questions about this good example? So the students who got a lower grade, some of them didn't bother doing a write-up. And it's hard to get a high grade if you're missing one of the 3 required components of the submission, being the summary table, hand calculations, and written verbal description, or like narrative description of your assumptions, calculations, and data sources. So some people didn't bother with the write-up. They did poorly. Some people used like lined notebook paper for their calculations, and it just was terrible and hard to follow because the equations are very often bigger than the space provided by lined notebook paper, and some people didn't include the units. It was just a bunch of random numbers that are impossible to follow if you don't know what the units are. Some people who did poorly didn't break it up into clear sections, and so it was just page after page of calculation, but it was never really clear if we're talking about the sports stadium, the box factory, the food processing plant. So there has to be context. Even though I'm familiar with the project, it's still easy to lose track of what your calculations refer to if you don't take me through it in a really explicit way. All right, so if you have questions as you're working on the project, please feel free to come see me. I'd be happy to help you out. All right, well, we are going to watch a video. This video now is about 10 years old, but it's still pretty relevant. How many of you have a Casio calculator? Almost everybody's hand is, actually everybody's hand is raised. I think you had to get one when you were in 111, right? That was the standard calculator in 111. I'm not a huge fan of the Casio calculator, but it's pretty good for the fact that it's under $20, and it is allowed for use on the FE exam. So I guess that's maybe another factor in its favor. So what this video shows is how to solve Manning's equation for unknown flow depth using the Casio calculator. So you should follow along. This video was recorded by Bill Pearson, who's an electrical engineering professor here at Marshall for a number of years. He's kind of the guy who started engineering at Marshall in its current state. And all right, without any further delay, let's watch this video. And I'd encourage you to follow along because it'll help a lot. So the link to that video is posted on Blackboard. If you need to go back to it again later, I'd encourage you to look through it. This method of being able to translate a formula into something that you can enter into the calculator. So you're reassigning variables and then you're rewriting the equation with those reassigned variables. Getting comfortable with that will make this big assignment that I've told you about for next week a lot easier. And in fact, this issue is not going away. It's not just Manning's equation that you're going to have to solve in the Casio calculator. There are some other complicated equations that we're going to do for non-uniform flow, where it's the same kind of thing, where we've got, you know, a complicated cubic equation that you need to find the roots for, or we're solving for a variable that exists in multiple locations in an equation. So we'll work a couple of problems today where you can either use your Casio, or we'll also go through the process of trying out Wolfram Alpha, and we'll also do the same thing with Microsoft Excel, just so that you've got your bases covered in terms of numerical solving tools. All right, now one thing I need to mention is that so far we've only looked at Manning's equation in terms of SI units. So in terms of SI units, here's one form of the equation where we're solving Manning's equation for flow rate rather than velocity. And remember that oftentimes I've said what we'll do instead of having the hydraulic radius and the area separate is we'll just combine them together. So it's area to the 5/3, slope to the 1/2, end value times wetted perimeter to the 2/3. So this is for SI units. But if you've got British gravitational units or US customary units where we're working in terms of feet and cubic feet per second for the flow rate, then there's this coefficient in front for the units conversion of 1.49. Actually, technically, I think it's 1.486, but most of the time people will just write that as 1.49. And so be sensitive to the fact that if the problem is given in traditional units, you need to just add this 1.49 in order to get the correct answer. We can further rearrange the equation if we're going to use Excel for our numerical problem solving. And the reason why this is beneficial to rearrange the equation in the way that it's written here is that all of the constants, if we're solving for the flow depth, are on the right-hand side of the equation. So the roughness of the material and the corresponding end value would be a constant. If the flow rate is given and the slope is known, then all of these terms on the right-hand side of the equation would be constant, and we're just trying to solve what is the depth that gives us that value on the right-hand side. So what we can do in Excel is take a guess of the y value, see what is the left-hand side of the equation, and keep changing the guess until the left-hand side of the equation equals the right-hand side of the equation, and the difference is 0. So we'll use GoalSeek as a pretty useful tool to solve for the depth in Excel. Any questions? All right, well, let's try this one. Let's say that we have this channel which is 15 meters wide across the bottom. It has 2-to-1 side slopes where the 2 is the width, 1 is the vertical component of the side slopes. And we're passing 175 cubic meters per second through this channel. It's laid out on a slope of 0.45%, and then the end value is 0.013. So if you have put Manning's equation into your calculator along with the video just now, you should be able to update this pretty easily, because all you'll have to do is, you know how he was going through the part where it was asking you to define the flow rate, the slope, the end value. You just put in these new values for flow rate, slope, and n, and, well, t, if that's any different, and find out what's the flow rate. I don't have a Casio emulator on here, so instead I'll solve this one with Wolfram Alpha. And you're welcome to follow along if you've got your laptop. You can follow along on Wolfram Alpha if you'd like. Okay. So let me just try and get both of these displayed at the same time. All right, so I'll say we've got 175 is the flow rate, and then the way that we're going to write the area here, if the bottom width is 15, then it's 15 plus 2y, because t is 2 in this formula, and then that is multiplied by y, and then all of that is to the 5/3 power. Then we've got a slope of 0.0045 to the power of 1/2 divided by 0.013, and then the wetted perimeter is 15 plus 2y, 1 plus 2 to the power of 2, all of that is to the 1/2 power, and then the wetted perimeter is to the power of 2/3. Lots of places to mess this up. We'll definitely have to focus on attention to detail. And if you notice me typing anything in wrong, then for sure call it out. Help me avoid the mistake. So I'm going to type in 175 is equal to 15 plus 2y times y, and then that is to the power of 5/3 times 0.0045 to the power of 1/2. Okay, and then all of that is going to be divided by, I'll use this fraction symbol here. Oh, no, that's not what I want. I think I maybe have to select it all, and then I can tell it to divide by. That didn't do it. Oh, I seem to have locked up the window here. I shouldn't have. Not responding. Let me wait just a moment longer. I broke the internet. All right, that's okay. When in doubt, just throw it all out and start from scratch. I guess that's how they encourage you to pay for the upgraded premium service. What we're doing is free. They do have a paid tier. Let me start over here. 175 is equal to 15.
You might have to click the fraction button, and you can probably select where you put what you put on top and one on the bottom.
I'll give that a try, but that's not how I was doing it before class. Yeah, maybe my problem is using the Microsoft browser. I'll just cross my fingers and hope I get lucky this time. To the power of 5/3. Okay, here's the moment of truth. No, that wasn't what I wanted. Dang! Okay, now what was your suggestion to do this? You know, what I can do is I guess maybe just copy all of this and paste it into the numerator box over there. Maybe I should have started with that since I knew that I was going to have it to begin with. There it is. All right. 0.013 times 15 plus 2 times y, 1 plus 2 squared. I mean, some of this I don't necessarily have to do in Wolfram Alpha. I could have just known that. Like inside the parentheses there is 5. 2 squared plus 1, but we'll do full bore, have it handle every calculation. All right, now I think I'm ready for the 2/3 power, and then we'll let it rip to calculate what is the y value that makes all of this on the right-hand side equal to 175. So compute the input, give it a moment. See what it came up with. We get a graph, we get a bunch of stuff, 1.752. 572. Yeah, that's right. So y equals 1.572 meters. Sometimes you'll see the answer expressed this way. It'll say y sub n. Anybody know what the n stands for? It means normal. This is called the normal depth. The normal depth is the depth that it normally would be if conditions are steady and uniform. If conditions are unsteady because you've got some other obstacle or a different slope downstream or the flow rate is changing over time, then you won't have the normal depth. Normal depth is just for steady uniform flow. All right, so now let's try this with Excel. And honestly, I think it'll be less tedious than Wolfram Alpha was just now. Did anybody solve it in the Casio and get that? 1.75, yes? A couple of thumbs up there. That's good. Okay, so here's what we'll do in the spreadsheet. I'm just going to paste this equation into the spreadsheet because this is the way I'm going to solve it in the spreadsheet. Okay, so I want to know the flow rate and the width of the channel. By the way, I initially typed capital B, but I changed it to lowercase b. Why does it matter? Anybody remember what's the difference between lowercase and capital B?
The lowercase b is your bottom and capital B is your total.
Very good.
Rising
That's exactly right. Lowercase b is the bottom width, capital B is the top width. So I don't want there to be any doubt that what I'm referring to here is the bottom width. Okay, so the flow rate, the bottom width, and then all these other parameters. So let me just put in the details here. Our flow rate's 175. And the bottom width is 15 meters, the n value 0.013, the slope of the channel 0.0045, and then the side slope of the trapezoids is 2 horizontal to 1 vertical. Okay, now I need to calculate the W term. Do you remember from this table 10.1 that we've seen before? Let me copy that into the spreadsheet. So for a trapezoidal channel, we're going to need to kind of have this intermediate calculation of W, which we use to find the wetted perimeter. So W, the wetted perimeter factor, is going to be equals 1 plus T squared to the power of 0.5. All right, so we've got W determined. And then we're going to have to put in some guess for the Y value in meters. So let me just start off with a guess of 1 meter. So this is the flow depth. Initially guess, then iterate until convergence. Okay, and with that guess, we're going to calculate the area of the channel in meters squared, the wetted perimeter in terms of meters, and then the hydraulic radius, which is also in terms of meters. Okay, so if the depth is 1, then what would the area be for a trapezoidal channel? It would be B plus Ty, and all of that multiplied by y. So equals b plus t times y, and then all of that is multiplied by y. Okay, so this is what the area would be if the depth is 1. It's not going to be 1 in the end, but it's a fine starting point for now. Okay, likewise, we need to calculate the wetted perimeter. So wetted perimeter is b plus 2 times y times w. So we're just using these geometric parameters from table 10.1 on the basis of our initial guess. And then hydraulic radius is defined as area divided by wetted perimeter. Okay. Now, this is where this formula comes in. Because what I want to determine is what's the left-hand side of that formula and what's the right-hand side of that formula, and then guess the depth until the two are equal. So I'm going to say there's the left-hand side of the equation, there's a right-hand side of the equation. So the left-hand side is area to the power of 5/3 divided by the wetted perimeter to the power of 2/3. So that's the left-hand side of the equation. And the right-hand side of the equation is n times q divided by slope to the power of 0.5. Okay, so let me just go to the left-hand side and the right-hand side one more time. What we've got on the left-hand side is area to the 5/3 divided by wetted perimeter to the 2/3. And then the left-hand side is always going to be changing because it has the variable, it's dependent on the variable of y. Y is always going to be changing. Whereas the right-hand side is a constant because when we change the depth y, that's not going to impact n, q, or the slope. So what I want to find is the difference between the two, left-hand side minus the right-hand side. And my goal is to find what is the y value that brings the difference between the two down to 0. So if I say 1.1, do I get closer? Yeah, that's an improvement. 1.2, that's an improvement. What about 2? I went too high. I overshot. 1.9. All right. So what I'll do instead of the hunt and peck trying to achieve convergence is I'll, in the data tab, what if analysis, goal seek, I will set the difference to 0 by changing the flow depth. The difference is pretty close to 0, close enough because we only need to know the depth to maybe the nearest hundredth of a meter for our purposes. 1.573. That seems familiar. I do recall that from our prior calculation with Wolfram alpha, 1.573. So it works. Either way. So you've got a couple of these on that new homework assignment number 8. You'll just sail right through it. The people who missed today, maybe they won't sail through it. I hope it was worth your time to come. Any questions before we move on to one more? We've got 10 minutes. Let's try and get through this example. Same thing, trapezoidal channel. We've just got a different flow rate, a different T, different end value, different bed slope. So, I mean, everything's different, but the process is the same. So if you set up that spreadsheet, what I suggest you do is we could have this first sheet be example 1 from today. And then if we duplicate it, right-click, copy, create a copy. Now, we'll let this next one be example 2. All right, so what's new in example 2? Let's copy down the problem statement here, or the details anyway. So the flow rate is, I should have made this next example be in traditional units if I'd been thinking about it, because that's a curveball that you need to always be on the lookout for, is how do things change if it was traditional units. And so, like this, rearranging the equation, think about it when the 1.49 belongs by the area, because when we're in traditional units, then we have to multiply this part 1.49. So all we'd have to do to get this to work out is just multiply 1.49 by the left-hand side of the equation if it was traditional units. But it's not. It's another SI units problem. So let's update this one for SI units. It is 29 cubic meters per second. Looks like from the figure, the bottom width is 3.5 meters. The end value is a smooth asphalt, which they're rating at 0.014 for the end value. The bed slope is 0.1%. So that's 0.1 divided by 100. So it's 0.001. And then the side slope, it says it's 2.5 to 1 h to v. So that means that t is 2.51. I mean, sorry, 2.5. Okay, so it automatically updated our W value. It has the guess from the previous time we were running GoalSeek. That doesn't mean that this is the actual flow depth, because look, the difference isn't 0. So we're going to have to run GoalSeek again to find out what is the new value for the depth that causes this to converge. So let me do that again. Set the difference to 0 by changing our guess of the flow depth. Okay, so this is saying 1.658 meters, and that's what I have here. If you've got your calculator in Casio mode, you could do the same thing. Once you've got Manning's equation loaded into the memory, maybe you should just keep it in there for the whole semester, right? And all you have to do is just go back through, redefine S, N, B, T, Q, and then just solve whichever variable you're trying to find. It won't always be the depth that is the unknown. For instance, I might tell you what's the maximum roughness that could be tolerated in order to achieve a certain flow rate. So N could be the unknown in a problem like this. But here we got 1.66 is the flow depth. So, all right. Well, that is normal depth in a trapezoidal channel. Remember that the big thing on your mind right now should be the design project and demand estimation. I hope that you find it kind of interesting and fun. For a lot of you, this may be the first time that you've actually been through the design process. Design is different from analysis because it's an iterative process and you have to make assumptions. This is the real world where you don't know everything that you need to know in order to design, and so you have to sometimes start your design with a placeholder, just like a starting guess of what the value is going to be for now, and then maybe later on down the road you can update it if needed or when better quality data comes in. But if you do have any questions, feel free to stop by, and that's it for today. I will see you on Friday.